Here's a problem related to harmonic oscillator. This is out of the Atkins and DePaula text. The rotation of CH3 can be described as a potential of this form here. Looks like there's a cosine dependence. First part of the problem, show that for a small angle here, the motion is described by an harmonic oscillator. And here's a hint, expand cosine theta in in this case phi, cosine 3 phi, in a Taylor series about phi equals 0. Okay, well, before we start that, let's actually look at this function. Here it is. I plotted here potential versus phi, that's that angle, and cosine of that of 0 degrees is 1, but this is 1 minus, and so when phi is equal to 0, this term is 0. So this looks like the potential function, goes up and down like this, and it's, as stated in the problem, says this is the potential function you get for rotation about a CH3 bond. Let's look at that in a little more detail. Here is the CH3 group, and let's connect that to another CH3 group. And now let's rotate this and look down the carbon-carbon bond. So that means that we'll have a carbon here, and then a carbon right behind here. Here's the hydrogens that are bound to this carbon, and then behind in the other carbon there's some hydrogens bound there. And what we're doing here is going to rotate this about some angle phi. Well, this you may remember from organic chemistry. You can have a staggered or eclipse conformation. Eclipse would be when these hydrogens are right on top of one another. You rotate. And the staggered would be as drawn here, where this hydrogen in back is in between these two hydrogens in the front. So that means that, well, let's go back to our potential function, and let's see, when phi is equal to 0, you get a minimum in potential. So that means that this must be phi equals 0 when it's in the staggered conformation. As you rotate it up to 60 degrees, so rotate it 60 degrees, you'll get something that is high potential energy, and so on. So that seems to follow along here, so it goes up and down, and so this would be the staggered conformation when phi is 120, 0, and plus 120. And the eclipse will be when phi is equal to 180, 60, or minus 60. And so this really is sort of the potential energy function we expect for rotation of a CH3 group about a CC bond containing another CH3 group. So the problem asks to show for small values of rotation, phi, that this section here is described by an harmonic oscillator. All right, well, let's go see here. Recall that the potential for harmonic oscillator is 1/2 kx squared. And now here, this is the harmonic oscillator. And now here we have the potential for that rotation about a CC bond is V0, 1 minus cosine of 3 phi. And let's rewrite that as V0 minus V0 cosine of 3 phi. And we want to show for low values of phi near 0, this will reduce to V, goes as a harmonic oscillator, so there'll be some constants times phi squared. That's what we want to show. Let's take the suggestion in the problem and apply Taylor series. Let's first review what a Taylor series is. Taylor series says that any function, let's make a function of x, can be represented as the sum, if I goes to 0 to infinity, of the ith derivative of that function with respect to x. And we're going to expand about a particular point. So expand about, say, x equal x0. So we evaluate this derivative at x equal x0, and this then is multiplied by x minus x0 raised to the ith power divided by I factorial. There is the Taylor series. Taylor series expansion is our friend. Now let's look at the first few terms, and we're going to use f of x now. We're going to use the potential, we said, so v of phi, so we're changing our independent variable from x to phi. That's equal to v0 plus, that would be a minus v0 cosine 3 phi. So let's take the first, say, three terms here. We'll take I equals 0, I equal 1, and I equal 2, and we'll form those terms in the Taylor series. Let's take the I equal 0 term. This means that the zeroth derivative of a function, this is now v of phi. Well, let me be explicit and write v of phi. So this will be the zeroth derivative of v of phi with respect to phi. And we're going to evaluate this derivative at phi equals 0. So you want to expand about small values of phi and show it's a harmonic oscillator. All right, well, the zeroth derivative of the function is just that function where you have phi equals 0 here. So we'll just write down that as v0 minus v0 cosine of 3 times 0. We're going to evaluate phi is 0, okay, and that's just equal to 0. Oh, that's convenient. First term is 0. Let's try the I equal 1 term. So that's the I equal 1 term in the Taylor series expansion. We'll take the first derivative of v of phi, that's our function, with respect to our independent variable phi, and then once we get the derivative, we'll evaluate at phi equals 0. All right, so let's take the first derivative. Well, this term will go to 0, that's just a constant. This term, derivative of cosine, is minus the sine, so this comes out to be just v0 times 3 times minus sine, but there's a minus sign here, so a minus minus will give this a plus, sine of 3 phi. And again, we're going to evaluate this at phi equals 0. The sine of 0 is, well, it's 0, so wow, that's kind of cool. So the first two terms in the Taylor series expansion of our function is just 0. Well, let's do the third term. That would be the I equal 2 term. That means take the second derivative of our potential v of phi with respect to phi and evaluate that derivative at phi equals 0. All right, we take the second derivative. I'll let you do that by yourself, but what I get is 9v0 times cosine of 3 phi. And now we want to evaluate this at phi equals 0. So this comes out to be, well, cosine of 0 is 1, so this just comes out to be 9v0. Okay, well, let's see. So now we have the first non-zero term in that expansion, I equal 2. So we'll go back here. I equal 2, this will mean x minus x0, or phi minus phi 0, and phi 0 is 0. So this would just be phi, I is 2, phi squared, divided by 2 factorial. Okay, so this would just be phi squared divided by 2 factorial, which is just 2. So this is what the second term in the Taylor series expansion is. So now we have our potential function, v of phi, expanded to second order in the Taylor series is just 9v0 over 2 times phi squared. Now we compare this with a harmonic oscillator. We have v of x, that's a harmonic oscillator, is 1/2 kx squared. So here we have a phi squared, here we have an x squared. Oh look, it's a harmonic oscillator potential where if we equate these two, 1/2 kx is equal to 9/2 v0. Or in other words, that should be 1/2 kx is 9v0, or in other words, k is 9v0. So we've done what we set out to prove, that for small oscillations around phi, we expand the Taylor series around phi equals 0. That will give us a potential which is just like the harmonic oscillator, where the harmonic oscillator force constant, or the spring constant, is equal to 9V0, which is the maximum, or half the maximum of the potential. Let's look at part B. Now we have to derive an expression for the energy level spacing between the n equals 0 and n equal 1 states. Well, an easy way to do this, now that we have the harmonic oscillator correlation here, is to look at the Hamiltonian for the harmonic oscillator and compare that with the Hamiltonian for this potential, this rotation potential, contrast and compare and see if we can easily write down what the spacing of energy levels is. Let's do that. For harmonic oscillator, the Hamiltonian is minus h bar squared over 2m. The second derivative with respect to x, plus that potential, which is 1/2 kx. For the rotation, the harmonic oscillator is minus h bar squared over 2m. The derivative with respect to the derivative with respect to phi, plus it was 9/2 V0 times phi. That's the potential for the rotation. And, oh, look at that. We say that, okay, so 1/2 kx squared is 9/2 V0. So when we solve this, those are constants. So when we solve this rotation, we'll get exactly the same things we did for the harmonic oscillator. And so we can immediately write down what the energy level spacings were. So for the harmonic oscillator, I'll abbreviate that HO. Harmonic oscillator, for example, the n equals 0 and n equal 1, we had energy level spacings to be equal to h bar omega. And these energy level spacings were the same whenever you go up by 1 in quantum number. For the rotation about the bond, this, just to not be confused, rotation about bond, so that's not rotation of a molecule, rotation about a CC bond of the CH3 group. So rotation, well, what can we do there? Again, we'll get the same quantum numbers, n equal 1, n equals 0, so on, because we have exactly the same kind of equation for the harmonic oscillator and the rotation about the bond. And this will be also h bar omega, where we said that omega is the square root of k over m. And from this thing here, k is equal to 9V0. If we substitute this in, omega is equal to 9V0 over m square root. So it's exactly the same thing, except now we've used something different from omega for the rotation because of this equality of Schrodinger equation here, that if we replace omega by square root of 9V0 over m, where m is the mass that's rotating about that bond, then we get an energy level spacing like that. Taylor's series is our friend.